In our previous lesson, we introduced you to graphs. We defined graph as a mathematical or logical model and talked about some of the properties and applications of graph. Now in this lesson, we will discuss some more properties of graph. But first, I want to do a quick recap of what we have discussed in our previous lesson. A graph can be defined as an ordered pair of a set of vertices and a set of edges. We use this formal mathematical notation G equal VE to define a graph. Here V is set of vertices and E is set of edges. Ordered pair is just a pair of mathematical objects in which order of objects in the pair matters. It matters which element is first and which element is second in the pair. Now, as we know, to denote number of elements in a set, that we also call cardinality of a set, we use the same notation that we use for modulus or absolute value. So this is how we can denote number of vertices and number of edges in a graph. Number of vertices would be number of elements in set V and number of edges would be number of elements in set E. Moving forward, this is how I'm going to denote number of vertices and number of edges in all my explanations. Now, as we had discussed earlier, edges in a graph can either be directed, that is one-way connections, or undirected, that is two-way connections. A graph with only directed edges is called a directed graph or digraph, and a graph with only undirected edges is called an undirected graph. Now, sometimes all connections in a graph cannot be treated as equal. So we label edges with some weight or cost, like what I'm showing here. And a graph in which some value is associated to connections as cost or weight is called a weighted graph. A graph is unweighted if there is no cost distinction among edges. Okay, now we can also have some special kind of edges in a graph. These edges complicate algorithms and make working with graphs difficult, but I'm going to talk about them anyway. An edge is called a self-loop or self-edge if it involves only one vertex. If both endpoints of an edge are same, then it's called a self-loop. We can have a self-loop in both directed and undirected graphs, but the question is, why would we ever have a self-loop in a graph? Well, sometimes if edges are depicting some relationship or connection that's possible with the same node as origin as well as destination, then we can have a self-loop. For example, as we had discussed in our previous lesson, interlinked web pages on the internet or the World Wide Web can be represented as a directed graph. A page with a unique URL can be a node in the graph, and we can have a directed edge if a page contains link to another page. Now we can have a self-loop in this graph because it's very much possible for a web page to have a link to itself. Have a look at this web page, mycodeschool.com/videos. In the header, we have links for workouts page, problems page, and videos page. Right now, I'm already on videos page, but I can still click on videos link, and all that will happen with the click is a refresh because I'm already on videos page. My origin and destination are same here. So if I'm representing World Wide Web as a directed graph, the way we just discussed, then we have a self-loop here. Now the next special type of edge that I want to talk about is multi-edge. An edge is called a multi-edge if it occurs more than once in a graph. Once again, we can have a multi-edge in both directed and undirected graphs. First multi-edge that I'm showing you here is undirected and the second one is directed. Now once again the question, why should we ever have a multi-edge? Well, let's say we are representing flight network between cities as a graph. A city would be a node and we can have an edge if there is a direct flight connection between any two cities. But then there can be multiple flights between a pair of cities. These flights would have different names and may have different costs. If I want to keep the information about all the flights in my graph, I can draw multi-edges. I can draw one directed edge for each flight, and then I can label an edge with its cost or any other property. I just labeled edges here with some random flight numbers. Now, as we were saying earlier, self-loops and multi-edges often complicate working with graphs. Their presence means we need to take extra care while solving problems. If a graph contains no self-loop or multi-edge, it's called a simple graph. In our lessons, we will mostly be dealing with simple graphs. Now, I want you to answer a very simple question. Given number of vertices in a simple graph, that is a graph with no self-loop or multi-edge, what would be maximum possible number of edges? Well, let's see. Let's say we want to draw a directed graph with 4 vertices. I have drawn 4 vertices here. I'll name these vertices V1, V2, V3 and V4. So this is my set of vertices. Number of elements in set V is 4. Now it's perfectly fine if I choose not to draw any edge here. This will still be a graph. Set of edges can be empty. Nodes can be totally disconnected. So minimum possible number of edges in a graph is 0. Now if this is a directed graph, what do you think can be maximum number of edges here? Well, each node can have directed edges to all other nodes. In this figure here, each node can have directed edges to 3 other nodes. We have 4 nodes in total, so maximum possible number of edges here is 4 into 3, that is 12. I have shown edges originating from a vertex in same color here. This is the maximum that we can draw if there is no self-loop or multi-edge. In general, if there are n vertices, then maximum number of edges in a directed graph would be n into n minus 1. So in a simple directed graph, number of edges would be in this range 0 to n into n minus 1. Now what do you think would be the maximum for an undirected graph? In an undirected graph, we can have only one bidirectional edge between a pair of nodes. We can't have 2 edges in different directions. So here the maximum would be half of the maximum for directed. So if the graph is simple and undirected, number of edges would be in the range 0 to n into n minus 1 by 2. Remember, this is true only if there is no self-loop or multi-edge. Now if you can see, number of edges in a graph can be really large compared to number of vertices. For example, if number of vertices in a directed graph is equal to 10, maximum number of edges would be 90. If number of vertices is 100, maximum number of edges would be 9900. Maximum number of edges would be close to square of number of vertices. A graph is called dense if number of edges in the graph is close to maximum possible number of edges. That is, if the number of edges is of the order of square of number of vertices. And a graph is called sparse if the number of edges is really less, typically close to number of vertices and not more than that. There is no defined boundary for what can be called dense and what can be called sparse. It all depends on context. But this is an important classification. While working with graphs, a lot of decisions are made based on whether the graph is dense or sparse. For example, we typically choose a different kind of storage structure in computer's memory for a dense graph. We typically store a dense graph in something called adjacency matrix. And for a sparse graph, we typically use something called adjacency list. I'll be talking about adjacency matrix and adjacency list in next lesson. Okay, now the next concept that I want to talk about is concept of path in a graph. A path in a graph is a sequence of vertices where each adjacent pair in the sequence is connected by an edge. I'm highlighting a path here in this example graph. The sequence of vertices A, B, F, H is a path in this graph. Now we have an undirected graph here. Edges are bidirectional. In a directed graph, all edges must also be aligned in one direction, the direction of the path. A path is called simple path if no vertices are repeated. And if vertices are not repeated, then edges will also not be repeated. So in a simple path, both vertices and edges are not repeated. This path A, B, F, H that I have highlighted here is a simple path, but we could also have a path like this. Here, start vertex is A and end vertex is D. In this path, one edge and 2 vertices are repeated. In graph theory, there is some inconsistency in use of this term path. Most of the time when we say path, we mean a simple path. And if repetition is possible, we use this term walk. So a path is basically a walk in which no vertices or edges are repeated. A walk is called a trail if vertices can be repeated but edges cannot be repeated. I'm highlighting a trail here in this example graph. Okay, now I want to say this once again. Walk and path are often used as synonyms. But most often when we say path, we mean simple path, a path in which vertices and edges are not repeated. Between two different vertices, if there is a walk in which vertices or edges are repeated, like this walk that I'm showing you here in this example graph, then there must also be a path or simple path, that is a walk in which vertices or edges would not be repeated. In this walk that I'm showing you here, we are starting at A and we are ending our walk at C. There is a simple path from A to C with just one edge. All we need to do is we need to avoid going to B, E, H, D and then coming back again to A. So this is why we mostly talk about simple path between two vertices. Because if any other walk is possible, simple path is also possible, and it makes most sense to look for a simple path. So this is what I'm going to do throughout our lessons. I'm going to say path, and by path I'll mean simple path. And if it's not a simple path, I'll say it explicitly. A graph is called strongly connected if in the graph there is a path from any vertex to any other vertex. If it's an undirected graph, we simply call it connected. And if it's a directed graph, we call it strongly connected. In leftmost and rightmost graphs that I'm showing you here, we have a path from any vertex to any other vertex. But in this graph in the middle, we do not have a path from any vertex to any other vertex. We cannot go from vertex C to A. We can go from A to C, but we cannot go from C to A. So this is not a strongly connected graph. Remember, if it's an undirected graph, we simply say connected, and if it's a directed graph, we say strongly connected. If a directed graph is not strongly connected, but can be turned into connected graph by treating all edges as undirected, then such a directed graph is called weakly connected. If we just ignore the directions of the edges here, this is connected. But I would recommend that you just remember connected and strongly connected. This leftmost undirected graph is connected. I removed one of the edges and now this is not connected. Now we have two disjoint connected components here, but the graph overall is not connected. Connectedness of a graph is a really important property. If you remember, intra-city road network within a city that would have a lot of one-ways can be represented as a directed graph. Now an intra-city road network should always be strongly connected. We should be able to reach any street from any street, any intersection to any intersection. Okay, now that we understand concept of a path, next I want to talk about cycle in a graph. A walk is called a closed walk if it starts and ends at same vertex, like what I'm showing here. And there is one more condition. The length of the walk must be greater than 0. Length of a walk or path is number of edges in the path. Like for this closed walk that I'm showing you here, length is 5 because we have 5 edges in this walk. So a closed walk is a walk that starts and ends at same vertex, and the length of which is greater than 0. Now some may call closed walk a cycle, but generally we use the term cycle for a simple cycle. A simple cycle is a closed walk in which other than start and end vertices, no other vertex or edge is repeated. Right now what I'm showing you here in this example graph is a simple cycle, or we can just say cycle. A graph with no cycle is called an acyclic graph. A tree, if drawn with undirected edges, would be an example of an undirected acyclic graph. Here in this tree we can have a closed walk, but we cannot have a simple cycle. In this closed walk that I'm showing you here, our edge is repeated. There would be no simple cycle in a tree. And apart from tree, we can have other kind of undirected acyclic graphs also. A tree also has to be connected. Now we can also have a directed acyclic graph. As you can see here also, we do not have any cycle. You cannot have a path of length greater than 0 starting and ending at the same vertex. A directed acyclic graph is often called a DAG. Cycles in a graph cause a lot of issues in designing algorithms for problems like finding shortest route from one vertex to another. And we will talk about cycles a lot when we will study some of these advanced algorithms in coming lessons. For this lesson, I'll stop here now. In our next lesson, we will discuss ways of creating and storing graph in computer's memory. This is it for this lesson. Thanks for watching.